Hello and welcome to another installment of Geology 1 Processes and Products Lab DVD. In this section we will talk about plate tectonics, a general overview of plate tectonics, the stresses associated with the plate boundaries, and we'll also look at a very general way to calculate the rate of movement using hotspots or interplate volcanism. As you might remember, we have three different types of plate boundaries. The first type of plate boundary is the divergent plate boundary. In a divergent plate boundary, the plates move apart in opposite directions. A new lithosphere is created. The most common type of divergent plate boundary that we think of is the one associated with mid-Atlantic spreading ridge. However, divergent plate boundaries can also start on continents. The Afar Triangle region off Africa, looking into the African Rift Valley, is a spot on the Earth where the continent is in the process of rifting. When rifting occurs over a long period of time, however, we do end up with first separation. We have faulting along that separation as the two plates move apart. We end up with a linear sea. We see that going on now in the Afar Triangle region. And finally, if divergence continues for a while, we end up with something like this, where we have a mid-ocean range right here, where the magma is upwelling and the two plates are moving off in opposite directions. New lithosphere is created. The magma rises up, is erupted onto the ocean floor in this case, and the two plates move off in opposite directions, a divergent plate boundary. Well, the opposite of that would be a convergent plate boundary. Instead of plates pulling apart or moving apart in opposite directions, with a convergent plate boundary, we have plates coming together. Now, there are different varieties of convergent plate boundaries. We have two different types of crust. We have a continental crust, which is much thicker and less dense than the oceanic crust, which is a lot thinner and more dense. So therefore, if we have a continental plate meeting an oceanic plate, what invariably happens is that the oceanic plate is subducted or moves underneath the overriding continental plate. Well, what happens if we have two oceanic plates meeting each other? In general, the one that is younger is less dense, and it will be the one to remain up, while the older, more dense plate is subducted underneath. There are a lot of factors, of course, which affect that. What if we have two continental plates approaching each other? Well, continental plates are too light, too low in density to be subducted. So instead, what we see with continental plates is that they are sutured together, and with a lot of crustal deformation, we end up shortening the crust. So not only are we going up with mountains, but we're also building mountain roots. So continental plates converging, we end up with very tall mountains, as in the case of India, ramming into the Asian continent and forming the Himalayas, still active and still going on today. With continental and oceanic, we have subduction of the oceanic plate, and with two oceanic plates, we have subduction as well. As you might imagine, in any of these cases, we are destroying lithosphere. We're not creating lithosphere, we are destroying it. A subducting plate will eventually undergo partial melting. Lithosphere is destroyed. Here is a diagram that shows a typical ocean-ocean convergent plate boundary, and you can see we have an oceanic plate here, another oceanic plate here. As the subducting plate moves into beneath the overriding plate and below this lithosphere, we have partial melting. The magma is less dense and will rise. As it breaks the surface, we can actually have the building of volcanoes, and a volcanic island arc will form off the surface of this overriding plate. The last type of plate boundary is a transform plate boundary. In this plate boundary, lithosphere is neither created nor destroyed. Now remember, divergent plate boundaries will pull apart. Convergent plate boundaries will come together, and if one of them at least is an oceanic plate, we get subduction. When we have transform plate boundaries, we have two plates sliding past each other in opposite directions. Now, A very famous transform plate boundary is the San Andreas Fault, but more of your transform faults are located at mid-ocean ridges. Because of the curvature of the Earth, we don't have a nice divergent plate boundary that just slices right through. Instead, we have spreading ridges, such as these, that are offset. Where we see the offset, we have a transform plate boundary. Why is that? Well, look at this one. We have lithosphere moving in this direction and lithosphere moving in this direction. Again, it's a divergent plate boundary. Down here in this segment, we also have lithosphere moving off in this direction and lithosphere moving off in this direction. Between these two segments, we have this lithosphere moving this way and this lithosphere below moving this way. The lithosphere is moving in parallel directions, and therefore this is a transform plate boundary. We can also see transform faults down here. We see them connecting a trench and an oceanic ridge. We don't only have to connect the different segments of a ridge. So the three types of plate boundaries again are divergent, convergent, and transform. And this generalized diagram shows you the different plate boundaries. For example, let's see if we can pick it out over here. My diagram's kind of cut off, but where you see the yellow meeting this tan color, this is a divergent plate boundary, the mid-Atlantic spreading ridge. We have subduction, where we see these nice dark lines here, and where we have some dashed lines, we actually see transform plate boundaries connecting some of these ridges. Here's a neat little diagram that kind of summarizes all of your plate margins in one nice little graphic. Here you see a divergent ridge. How do you know that? Well, we have crust moving here and here, pulling apart in opposite directions. Between these two segments, we have a transform margin because up here, crust moving this way, down here, crust moving this way. This area between the two ridges is a transform margin. And here we see a plate, an oceanic plate, being subducted below an overriding continental plate. We're kind of cut off here, but we would get partial melting and the magma would rise. In this case, it looks like we have a continent right here, and instead of having an island oceanic arc, we probably would end up with a volcanic arc that would run along the edge of the continent. Three types of plate boundaries. Now, what types of stress are associated with the three types of plate boundaries? When you have compressional stress, you have stress as two objects push against each other. Guess what? Compressional stress is commonly associated with convergent plate boundaries, because convergent plate boundaries also have two plates moving against each other. And this diagram shows what can happen with compressional stress. We can have folding and or faulting, depending on how deep the rock layers are and how pliable they are. We generally see folding at depth and faulting along the Earth's surface. Tensional stress is just the opposite. We see in this diagram that we have stress in which something is pulled apart in opposite directions. Tensional stress. And guess what? That's most commonly associated with spreading ridges and divergent plate boundaries. The slide will also show you what a common result is of this tensional stress. We have faulting, and it's a special kind of faulting. This is normal faulting. And finally, we have shear stress, in which the stress has two objects moving against each other in opposite directions, most commonly associated with transform plate boundaries. We don't see faulting as much or folding, but we do see deformation as these two layers move past each other. Of course, we could have breaking right along here. Shear faulting. Okay, intraplate volcanism describes tectonics, which activity is associated not at a plate boundary. We have three types of plate boundaries: divergent, convergent, and transform. And yet we see things like volcanoes, volcanic activity, in the middle of a plate. This can be explained by intraplate volcanism, or more commonly called a hotspot. Hotspots are stationary mantle plumes that rise out of the magma, out of the mantle, and they can actually be used to determine plate movements. They were used to determine plate movements before we had satellite positioning, and we were able to get more technical and precise movement solutions. Okay, this diagram shows the classic Hawaiian Island hotspot. You can see the magma plume here rising up and a series of islands and even seamounts that have been formed. In which direction was the plate moving? Well, we can date some of the rocks on these islands and see that the rocks over here are older than the rocks here. And we also know that the volcanoes are active on the Big Island. So, we know that at one point the island of Kauai was over this hotspot, and that's what formed the island. The magma rose up through the surface, was erupted onto the surface, and the volcano built. The plate continued to move. The hotspot stayed in the same location, and therefore we have a younger and younger and younger volcano being formed as the plate moves. Let's calculate just how much was moved, and we're going to do a very rough estimate here. Here's another diagram, an overhead of the islands of Hawaii. Let's see how much we've actually moved from, here we are at Kauai, and this says it is 5.1 million years old as far as formation of some of these rocks. And we have a little island that is being formed. It's not yet an island, I misspoke there. It's still below the surface. So its current age is now. So we're going to put this as 0 years before the present, and we'll put this one at the date that we have gotten from analysis at 5.1 million years. If we use the scale on the map to measure the distance, this is what we get. We see we have about 450 kilometers from the island of Kauai to this currently formed volcano right off the Big Island of Hawaii. And we're looking at a distance in time of 5.1 million years. So, what's the rate of movement? Again, this is a very rough estimate. We have 450 kilometers of movement of the plate over the stationary hotspot. We need to get that down into a measurable rate of movement. The plate doesn't move very quickly, a few centimeters, maybe a year. So here we have the conversion factor, 10 to the 3 meters per kilometer. Note that our kilometers are going to cancel out. Let's get to centimeters. So we know that for every meter we have 10 to the 2, or 100 centimeters. The meters are going to cancel out, and we end up calculating that at 450 times 10 to the 5th centimeters. The distance, time-wise, is 5.1 times 10 to the 6 years, or 5.1 million years. So, what's the rate of movement? If we have 450 times 10 to the 5th centimeters, and we divide by the number of years, 5.1 times 10 to the 6 years, we end up calculating about 8.8 centimeters per year average rate of plate movement. The mantle plume stayed in the same location. The plate moved over, and different volcanoes, different islands were formed as that plate moved in a northwesterly direction. So in review, we have 3 types of plate boundaries. We have convergent plate boundaries that are associated with compressional stress. We have divergent plate boundaries that are associated with tensional stress. And we have transform plate boundaries that are associated with shear stress. Interplate volcanism, or hotspots, describe those areas within plates in which there is a stationary mantle plume, and this can be used to determine plate movement. If you have any questions about the calculations or any questions about plate tectonics, please feel free to email your instructor. He or she will be happy to help you. Thank you for joining me. Bye.